Hello everyone. This is a quick tutorial to introduce you to mass spectrometry, which is a topic that the book sort of lightly covers in chapter 2, but I sort of wanted to highlight it a little bit more. Essentially, mass spectrometry is a technique that can be used to identify elements or identify compounds, and in order to do that, you have to obtain a sample of the compound or the element, and you have to introduce it into an instrument like the one shown in the schematic below. Now, mass spectrometers actually now come in a wide range of varieties. They don't all operate on the same principle. However, this is a fairly common type of mass spectrometer that we call a magnetic sector mass spectrometer. And I'll just briefly explain the way that these types of instruments work. Essentially here, at this end of the mass spectrometer, that's where your sample would actually be introduced into the instrument. In mass spectrometry, you're going to be analyzing your sample in the gas phase. And so for that reason, then your sample has to meet some requirements before it can actually go and be analyzed within the instrument. First off, as I said, since we're dealing with a gas phase sample, or at least we want a gas phase sample, then if we happen to have our sample in a different state, be it solid or liquid, then we're going to have to what we call volatilize the sample. And so there are a number of techniques for volatilizing solid samples. Some of them are somewhat complex and advanced, and so as a result I'm not really going to discuss them in detail. But suppose if I have a liquid sample, if I introduce it or inject it into the mass spectrometer here, then by the energy provided by this heated filament, I can actually evaporate off the liquid phase and actually go and obtain gas phase particles of my sample. In addition, we not only want a gas phase sample, but we want an ionized gas phase sample. And so what we're going to do is bombard our gas phase particles with an electron beam, and typically that is enough to actually allow us to get either positive ions or negative ions. Now, typically in terms of frequency of use, normally mass spectrometry is primarily carried out in the positive ion mode. You'll see samples ionized so that we get cations, much like the cations that we're seeing in this particular picture. They're chlorine cations. But it is possible and sometimes done to actually carry out mass spectrometry in the negative ion mode. And so once we have our ionized gas phase sample, then we want to eliminate any possibility that our gas phase ions might collide with air particles and thereby alter their path within the instrument. And so for that reason, then we have to actually apply a vacuum to the interior of the mass spectrometer so that the space is completely empty and the gas phase ions will actually have freedom to travel from one end of the instrument to the other without colliding with any air particles. Now, these yellow discs I will call electronic optics. In other words, what they are is they're charged plates that are meant to actually guide the ions through the instrument from one end to the other. And the beam of ions would then travel through the instrument, right, turn this corner through the final charged plate and the slit within it to the detector at the end of the instrument. And once it's detected, that generates a signal, and that signal can then be plotted on a graph. Now, if you notice in this particular picture, the chlorine 35 cation is making it all the way through to the detector, but if we take a look at the chlorine 37 cation, the chlorine 37 cation, unfortunately, is actually not striking the detector. Its path is not at the proper angle or the proper configuration to allow it to strike the detector. Now, that doesn't mean that we cannot detect the chlorine 37 cations. What it means is if we vary the magnetic and the electric fields of the instrument, then that can alter the path so that eventually the chlorine 37 can actually make it through the slit into the detector. And the chlorine 35 would then move off and collide against the wall of the detector itself. So essentially, when we have a sample when we actually apply mass spectrometry as a technique, what we're going to do is we're going to scan through a range of possible masses and generate a plot over all of those masses. And we get what's called a mass spectrum. And a mass spectrum looks more or less like this. If you notice, once again, on the x-axis here, this is mass to charge ratio. So basically the mass of the particle that we're analyzing divided by the charge of the ion that we created when we volatilized and ionized the sample. Now, more often than not, the charge on those ions is usually +1 if we actually have mass spectrometry being carried out in the positive ion mode, though that can vary, and I'll show you in the next slide how that can vary. But here, if you notice, we're trying to analyze the element oxygen. And if you recall, oxygen in its elemental form is O2. Well, basically, if we have O2 and we're successful and we get to ionize this oxygen gas, we'll have O2 with a positive charge. Now, if you recall, if we calculate the formula mass for oxygen when it's diatomic, that's 2 × 16 atomic mass units. And again, the charge, if we're looking at the mass to charge ratio, the charge here would be 1. So that would mean that if I have a signal that corresponds to a cation of diatomic oxygen, then the mass to charge ratio should be 32. And I do have a large peak at 32. Now, if you look at the y-axis, basically this particular mass spectrum is actually situated with the y-axis in units of relative intensity. All that means is it takes the biggest peak in the spectrum and calls the top of that peak 100%. Right? Now, if we take a look at this peak over here, that's a peak that occurs at a mass to charge ratio of 16. Now, if we think carefully, well, that could be caused if I have provided too much energy when volatilizing the sample, then it's entirely possible that I might inadvertently break this bond between the oxygen atoms in diatomic oxygen when I'm trying to ionize this sample of oxygen gas. If I do that, then basically I'm going to get monoatomic oxygen with a positive charge as well. Now, the formula mass for oxygen atoms is 16 atomic mass units. The charge on the cation that I created during the ionization process is 1. So that would mean that the mass to charge ratio for this particular particle would be 16. And so as a result, I have a peak for 16. And so you can see how the mass data that we get from these particles can sort of be traced back based on principles of charge and based on what we know already in terms of determining formula masses and atomic masses, so that we can understand the spectra that we're looking at. All right, now let's take a look at the mass spectrum of another element. Let's take a look at copper's mass spectrum. Now, if you notice, this spectrum is a little different than the one that came prior for a couple of reasons. First off, the y-axis is now not given in percent relative intensity. It's actually given in percent abundance. So this is actually going to give us abundance data for the isotopes of copper. Now, if we take a look, we have one peak at 65, one peak at 63. And if we take a look at the periodic table, we can see that copper's atomic mass is about 63.5. So what that means is chances are we have a copper 63 isotope and we have a copper 65 isotope. Okay? However, notice that we have two pairs of peaks. So where does this pair of peaks come from? Notice that the mass to charge ratio is 32.5 and 31.5. We also should make memory of the fact that copper can have a +1 charge when it's a cation, but if you recall, copper is a transition metal, so it can also have a 2+ charge. And so what that means is, let's take this mass to charge ratio. The mass to charge ratio is 32.5 for this signal, or this peak. Well, if copper has a 2+ charge, then that means the charge is 2, not 1 in the denominator. So that would mean, if I cross multiply this 2 against this 32.5, that means the mass of this isotope is still 65. That means that this abundance of 10% and that abundance of 21% should be added together, so that my copper 65 abundance, 10% plus 21%, that's actually 31% in abundance. If we take a look at this signal right here and we do the same thing, 31.5 times a charge of 2, that would actually be 63. And if that's the case, then that means that this abundance of 23% should be added to that abundance of 46%. So an abundance of 23% plus 46%, that means I have an abundance here of 69% for copper 63. And if I consult tables of copper isotopes, we see that indeed copper 63's abundance should be 69%, but copper 65 should have an abundance of about 31%, as we concluded when we examined the mass spectra data that we've seen on this slide. One last thing that I've shown you, or that I will show you, is how mass spectrometry can be used to identify compounds. So this is the mass spectrum of water. And if you recall, water has this Lewis structure. If you recall, I have 2 hydrogens and 1 oxygen in water, so if I calculate the formula mass of water, I should get a mass of 18 atomic mass units. Assuming that when we ionize, we get charges of 1 for all of the ions that we're analyzing in the mass spectrometer, when we're actually analyzing the mass spectrum of water, then that would explain why I have this peak at 18 mass per charge. That corresponds to the intact water molecule. But suppose that, like I mentioned earlier, suppose I provide an excess of energy during ionization and I break that bond between the oxygen that's central to the water molecule and the hydrogen that's on the other side of this green line. Well, hydrogen has an atomic mass of 1, and then this portion of the water molecule that's left behind would then have a formula mass of 17. And if you notice, I have a signal that corresponds to a mass per charge of 17 and a signal that corresponds to a charge of 1. If this happens again, and we break this bond as well, then I'll have 2 fragments with an atomic mass of 1, and the mass of the oxygen atom by itself would then be 16. Notice again, peak of 1, peak of 16. And so what this does is it creates sort of a mass spectral fingerprint for the water molecule, and this same line of reasoning can be used with other compounds to help identify them. When we actually get this breaking apart of a compound, when we try to go and measure the mass spectrum of it, this is actually referred to as fragmentation. And these fragmentation patterns are useful when trying to identify compounds. And so tomorrow, you're going to do an assignment for me where you apply some of these same principles to understand the mass spectrum of elements and compounds. Once again, I'll be navigating the room to see how you guys are doing and offering assistance. And we're also going to move on in Chapter 2, talk a little bit about nomenclature and the rest of the topics in that chapter. If anyone has any questions, then by all means, please ask in class tomorrow, and I'll see you guys then. All right? Have a good night.